recording has started. So, today, we get started on the next unit. And like I mentioned before, the next section dealing with energy, work, and power is another way for us to analyze motion. And so like I said, a lot of the things that we're going to do in this unit are going to seem familiar. Problems, labs, situations that we've dealt with before. But before, we looked at them from the standpoint of things like displacement, velocity, and acceleration, and then force to explain what was going on. But now we're looking at it from a different standpoint. These terms here, energy and work especially, are another way for us to just explain what's going on. Another way for us to look at an object and say, okay, what's happening here? Why is this happening? And then we can explain it that way. So, let's get a couple of definitions down first. Energy. Energy is a hard word to define, especially in the physics sense. There's one definition that's out there a lot that I really don't like, and we'll talk about that in a little bit and why I don't like it. But this definition I do kind of like, and that definition is the ability to cause a change in matter or the environment. So it's the ability to cause change, the ability to make things different than they were before. And that's how we define energy. Energy comes in a lot of forms, and we will talk more about those forms tomorrow in a little bit more detail. But one form of energy that we need to introduce now, and it's a form of energy that I think most of you are familiar with, is kinetic energy. And kinetic energy is the ability to change matter due to motion. So an object has to be moving. Kinetic energy depends on a couple of things. First, formula, 1/2 mv, and then that 2 is supposed to be squared. It's supposed to be 1/2 mv squared, but when I reformatted the slide, it took away my superscript. So 1/2 mv squared. Okay? And you'll notice that on our first slide of the day, we've already introduced something new. There it is, right? We broadened our horizons on the first slide of today. It's exciting. At least I think it is. So energy, the ability to cause a change in matter or the environment. And one type of energy that's out there is kinetic energy, the ability to change matter due to motion. So by virtue of the fact that something is moving, it can cause change in something else. We've already introduced an idea that relates to change. What idea have we sort of introduced already that relates to change or tells us about change? Acceleration, right? Acceleration being a change in velocity, specifically or more generally being, okay, what's happening to this object? Is it speeding up? Is it slowing down, right? Acceleration measures change. Energy is that ability to change. Okay? Good there? All right. For dramatic effects. No, wait. Oh, next term. Work. Okay? Work is one of those tricky ones because it's a word that you all know. It's a word that you've come across and you use pretty regularly. But in physics, it has a very specific definition. And if you're not familiar with that definition, it can get you into some trouble based on problems. So, definition of work. The transfer of energy between objects. The transfer of energy between objects. So this ability to cause change is going from one object to another object. Like it says here, the energy of an object will change when work is done. Because that's what the definition of work is, a change in energy. So work is, by definition, transfer of energy between objects, but a more practical application of that, energy of an object will change when work is done. Good there? So, the next slide is more for effect. You don't need to copy it down, but it's going to lead us to somewhere that's kind of important. So, first, kinematic equation. A kinematic equation that we've used quite a bit, right? One of our 4 kinematic equations. So the first thing I'm going to do, I'm going to take VI squared and move it to the other side of the equation. So now on the left-hand side of the equation here, I have VF squared minus VI squared. If I have final minus initial on the left-hand side, where is that taking us? Kind of, sort of. Change, right? Final minus initial is a delta thing, right? And we use it in a lot of different applications. But over here on the left-hand side, we're starting to get into change, okay? That's important. It's part of the definition of work. Over here on the right-hand side, we have, 2 is just a constant, and then we have acceleration and displacement. We said, though, that acceleration depends on a couple of things, right? What determines the what factors into the acceleration of an object? Well, that's how we measure it. What factors into it? That's what acceleration is, but what causes it? What determines how much acceleration we have? Force. That's how we measure it, but, okay? Net force and mass, right? We said those 2 factors determine the acceleration of an object. The delta V is how much acceleration it has, but the force and the mass are determining that value, okay? So, over here on the right-hand side, I'm going to change it to look like this, where all I did was take force and mass and substitute them into the expression for acceleration. Does that make sense how I made the jump from line 2 to line 3? I do a little rearranging, and I end up with this. Hopefully, these 2 formulas on the left-hand side look familiar. 1/2 mv squared. Take a look at your notes. You just wrote it down. That's the formula for what? Kinetic energy. Okay? But here, V final minus V initial, the left-hand side of this equation is telling us what? What did we say final minus initial gave us? Change. So this is the change in what? Change in, not velocity, kinetic energy. Because these are my 2 kinetic energy formulas. So the left-hand side of this equation is the change in kinetic energy, or the change in energy, right? Over here, if we're going to change the kinetic energy, I got to apply a force to that object. Why? Because how does velocity change? Only if I do what to it? If I apply a force, right? Push it or pull it. Okay? And that only works if that object actually moves because of what I'm doing. So, if this left-hand side is change in energy, what does that mean the right-hand side is probably going to tell you about? I heard it. Work. Because by definition, it's the first thing, or not the first thing you wrote down, it's the last thing you wrote down. What is work? A change in energy. Okay? So this equation relates for us the change in energy with the work that we do. So work is only accomplished if you do 2 things. What 2 factors determine the amount of work? Force and displacement. We'll go distance or displacement, kind of the same thing in this case. Okay? So you got to have 2 things, force and displacement. The amount of work that you do on an object depends on the force you apply to it, and then how much it moves because of what you apply to it. And that's how we change the energy of this object. All right. Good there? Okay. Like we do often in physics class, simple ideas, now we have to apply them in different situations. So the next 5 slides I have for you are pictures. If you can draw the pictures, obviously, or you can get these slides online. They're available there for you there if you would like. Okay, but I'm going to show you the picture. I'm going to ask you the question, give you a minute to discuss, then we'll come back and discuss as a group. Okay. So, first picture, a guy throwing a baseball. Is it work when someone throws a baseball? Discuss. 2 or 3 person groups, 1 minute, go. We could also throw the why part into it, because that's what I'm going to ask you to do later. So.
Yes, because he's putting his arm action, the arm action, the straight the more velocity you get out of the arm, the more velocity you get out of
Come on, buddy. Thanks for I'm dirty. Do you think I'm dirty?
What?
Is this what you got?
No, I actually haven't.
Okay, so short answer. 1, is it work when somebody throws a baseball?
Yes.
Yes. Okay. Now let's talk about the why. There's 2 ways that you can justify your answer of yes for is it work when somebody throws a baseball. Let's talk about it from the energy standpoint. What happens to the energy of this object? It increases, right? It goes faster than it was before, right? So the ball has more kinetic energy because of that applied force than it did before the force was applied. That's work. Energy has changed, okay? We said that the amount of work done depends on 2 factors. What were those 2 factors that we talked about? Force and displacement. Is a force being applied to this object? Is it moving because of that force? Yeah. So, force is applied, it moves under the influence of that force, therefore that's work. Okay. Good there? I'll give you a second to jot some things down if you need to. Good there? Okay, next picture. So, here's another baseball player. I'm not really sure. Nah. American Indian, possibly? Not really sure. Jamaican? Yeah, that's a ball. It just doesn't have stitches there. Okay. But this person, woman?
It's a
Yeah, I guess. Yeah. Although possibly up for debate, but you know. Anyway, so this person is catching the ball, but they are catching the ball in a way that you would catch that ball like you would catch a water balloon at like a family picnic over the summer, right? You got to catch it here, and you do the old scoop thing like this, okay? Is it work when somebody catches the ball? Yes or no? Discuss. Go.
Yes.
But why as well?
yeah, but the first one just stops. No, the person is moving.
The ball. It slows down. So they grab it.
But in baseball, it's just like that.
Okay.
So there's no one way.
Come on, Tom.
But in
All right.
actuality,
So let's discuss. So first, is it work? Yes.
okay.
So we said that there were 2 ways that we can justify that this is work. If we talk about it from an energy standpoint, what's happening to the energy of this object? It's decreasing, okay? But more generally, is the energy changing? Yeah. So because of the fact that the ball has less kinetic energy than it did before, it's still changed, therefore this is work. Okay. The other standpoint, if we look at the 2 factors that determine the amount of work, right? We said there were 2 things that determine the amount of work. What were they? Force and displacement. Is she applying a force to the object? Is it moving while she's applying the force? Yes. The only thing being, though, in order for her to slow that ball down, she has to apply a force in which way? Opposite direction. But it's still moving, and she's still applying a force. It just so happens to be that she's applying a force in the opposite direction. So the end result is a decrease in kinetic energy. but it's still work. All right, give you a couple seconds to jot some things down. Once again, remember, these slides are available to you online, so you can get those there. All right, good there? All right, next picture. This is one I'm sure a lot of you have experience with, because I know that a lot of you probably go home. Oh no, sorry, wrong picture. So my presentation got messed up. Anyway, so same person catching the same ball that was thrown as before. Okay, but in this case, no glove. She's just going to barehand it, right? Okay. Back before the white man came to this country, this is how they played it. So you know.
You have a point.
So
What are like leg? Like why are they like arrows?
those are stirrups. So decorative. So anyway, so 1. Is it work? Catching the ball in this fashion, is it work? Yes. Okay. So does it work? Yes. Why? If we go back to our two definitions, is she still changing the energy of the object? Yes. This ball has less kinetic energy after she catches it than before. Okay. If we talk about the other two factors, right? Before, when she did the whole water balloon and family picnic method, right? How far did that object move while she was applying the force? Pretty far, right? You catch it out in front of you here, you bring it all the way back here, right? In this case, how far does the ball move while she's applying the force? Not very far. As far as her hand squishes back like this, okay, which isn't very far. That being the case, we have to accomplish the same thing, right? The amount of work in this picture is exactly the same as the amount of work in the previous picture, assuming that the ball gets thrown with the same velocity. But there are two factors that influence work, right? What are they? Force and distance, right? Force and displacement. Here, the displacement is very, very small. So how much force does she have to apply? A whole lot, right? Hence the red hand indicating pain, right? It's the universal indicator of pain. So. But still the same amount of work, but depending on how much force we apply, the displacement involved, that will determine where we go to accomplish that work. Okay? Good there? Next picture. One that I know you're probably familiar with, because a lot of you probably go home and sculpt after school a little bit, you know, with blocks of marble. I'm assuming it's pretty popular pastime after school. So this guy needs
move his chair.
It's not his chair, it's his tools. Right? And maybe this sculpture has to be over here. Maybe.
Why would you sculpt it then move?
Well, if you're sculpting like a person or something, it's probably harder to move. But
It would be lighter though.
I mean, it would be lighter, that's true. But if it falls, then you end up with Venus de Milo, and that's not the intention. Maybe it's not the intention, I don't know. But anyway, but apparently wheels don't exist in this world, so all you can do is just lasso this big like block of marble and try to drag it across the floor.
Wouldn't it fall over?
See, it's the thing. Maybe it just needs to be over here, you know?
It doesn't look that big.
But it's a block of marble.
Yeah, but you think of
It's a
not
stone
big.
as big as a person.
It's not as big as a person though. He's crouching back.
That's true. Okay, it's a stone 2/3 as big as a person.
Okay, it's still really heavy though.
Anyway, the point being that this guy lassos this big block of marble.
He's pulling it wrong.
He pulls it really, 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 really hard, but he can't move it. Is this work?
Yes.
No. This energy.
No.
So,
No.
let's take a vote. No, this is not work.
Wait, let me do
Yes, this is work. Wait, let me think about it. All right. So, we said When I first introduced the concept of work to you, I said it's one of those things that's kind of tricky sometimes because you know what work means. Is this guy working hard by pulling on this block and not moving it?
Yeah.
Yes, but by the physics definition of work, has energy been transferred from this guy to this block? Is this block moving any faster or slower after he pulls it than before he pulled it? Is there any change in its kinetic energy? No. Okay? Okay, good.
What about like the SF max?
Okay. In this case, the reason why there's no work being done on it is because his force is not the only force that's acting on that object. So he is not doing work on that object because his force does not cause its energy to change, because it's not the only force that's acting on that object. Does that make sense?
Yeah, so I guess it's like the static friction.
Yeah, so in that case there, right, there's other forces that are influencing it. So, but he is not doing work on that object because his force is not causing its energy to change. Okay? If we could get rid of the static friction, yeah, he would do work. Is it a lot of work? Well, it depends on how much his energy changes, right? But in this case, because his force does not result in that energy changing, there's no work done. Right? So, no energy change, that's one way we can define it. But also, we said that there were two factors that are involved in this, right? What two factors are necessary for there to be work done on this object? Force and displacement. Is he applying force? But is there displacement because of his force? No. Good there? I'll give you a couple seconds to jot some things down. So I mean, that's where we get into, like, you know, analyzing this in another way. We would say this object doesn't move because the force is balanced, if we're talking about it from a force standpoint. From an energy standpoint, it doesn't move because he's not doing work on that object. The end result is the same. It doesn't move, but it just explains it a different way. Which is sort of the point with energy, is that, you know, we can look at those same things, but just explain them differently. All right, I'm going to skip the next picture and go to the final picture here. Okay. So in a similar situation, okay, apparently wheels don't exist in this world anywhere. Okay. So it's kind of ironic that you have to, like, you know, work hard to move the flexorciser. Maybe there's just a big block of granite inside of the box. That's what the flexorciser is. I don't know. All right. Is this work as this guy pulls on the box and he drags it across the room? Yeah. So is it moving? Yes, he's moving it across the room. So is it work? Yes. But. Okay. He's applying a force how in this picture? At an angle, right? But which way is the box moving? Horizontally. So is his whole force going to changing the energy of that object? We know that this force has components, right? Which component's going to do the work in this case? Only the horizontal component, because it's parallel to the direction of movement. So only forces or components of forces that result in a change in the energy do work. Right? If this object moves horizontally, only the horizontal component will do work. All right, we good there? So, calculating the amount of work done. In order to calculate the amount of work that's done, two factors, force and displacement. You multiply the two of them together. When you're dealing with force, we are dealing with magnitude. Work is a scalar quantity. It only tells you how much. How much what, specifically? How much energy? That's the word. How much energy change is there? Okay? So that depends on the force, but only forces that are parallel to motion. Okay? And it depends on the displacement. Now, you'll notice that it has no positive, negative, okay? Technically, that's true. But work can be negative. It might not come out negative from this calculation, but what would negative work do to an object? Slow it down, or if we talk about it from an energy standpoint, it would decrease the amount of energy that an object has. So the person catching the ball from the previous pictures is doing work, but is doing negative work. How would you have to apply the force in order to do negative work? How do you have to apply a force to slow something down in relation to its motion? You have to apply your force in the opposite direction. Okay? Is that good there? So, work is a scalar. Doesn't have direction, but it can be positive or negative depending on what it does to the energy of that object. And if you go back to that rearranging of the kinematic equation, depending on what VF and VI are, you can get a negative number there. Remember, scalar quantities don't have direction. That doesn't mean they can't be positive or negative. We use the positive and negative on a vector quantity to indicate direction, but scalars can be negative too. It just means that something is decreasing. It's going down. The amount of energy that an object has decreases. That means negative work. So there's our introduction to work and energy. That's the basics. We're going to build on that stuff over the next couple of weeks, talk about it in terms of different kinds of energy, different kinds of work. Right? There is some homework on the calendar for this evening. A lot of it is conceptual, so if you want to take a look at it, we'll do some of that stuff over the next couple days in class as well. Okay? But take a look at some of that stuff from the book as far as homework goes. Okay?